Have you ever wondered why math works? Ever since elementary, we've learned about how these numbers interact, like 1 plus 1 equals 2, 2 plus 2 equals 4, or e to the pi I plus 1 equals 0. But why does 1 plus 1 equal 2? Well, 300 pages of pure logical deductions can tell you, but even that isn't absolute. The absoluteness of math comes from the fact that it's an axiomatic system. This means that through logical rules, factual statements can be made from base axioms. Now, an axiom is like a mathematical fact, but it's something that we can't prove to be true. For example, in arithmetic, an axiom is 0 is a number. Another axiom would be the number after a number is also a number.
But there's one fundamental problem with the axiomatic method. It is completely and utterly reliant on the truth of the axioms. Thus, if the truth of the axioms falls through, then the truth of the whole system collapses.
This made mathematicians worried. They started to formalize the internal structure of mathematics in order to make sure that there were no inconsistencies. This brought forth the Principia Mathematica, a 3-volume book that comprised all of arithmetic and condensed it into pure logic. This was as if someone were to take all of the language and the grammar of the English language and the definitions of the words that we use to describe the English language and brought it into one book. The Principia Mathematica was meant to help mathematicians prove the internal consistency of the axioms of mathematics. But in 1931, Kurt Gödel published his incompleteness theorems, which proved this wasn't possible. Firstly, he created an axiomatic system that he used to describe mathematics. Let's call this GS. This meta-mathematical language had its own symbols, axioms, and deductive logic. For example, the symbol C stood for if A, then B. Or equals meant two symbols were equivalent. And 0 stood for, well, 0. This is like defining a language to describe English. For example, word, sentence, conjunction, these are all words that describe English. GS also had its own punctuation system. Next, he gave each word a number, and each statement or sentence a number as well. These were called Gödel numbers. For example, the statement 0 equals 0 would have its own Gödel number. This way it would work where each of the words he created would have their own ID. He would then get in ascending order the primes and would raise them to the power of each symbol. This meant that every meta-mathematical statement could be translated into arithmetic. Thus, the properties of the statements in GS would apply to all of arithmetic. With this, he created a statement that said, the statement X can't be derived using the rules of GS. This statement had a Gödel number. Let's call it X. And with this, he defined the statement X as, the statement with a Gödel number of X can't be derived using the rules of GS. This statement also has a Gödel number, and thus the pattern continues. He then proved that X could be derived if and only if the opposite of X was derivable. Meaning you could only logically deduce a statement like, right now it's morning, if you could also logically deduce that it's night. This meant that if GS were consistent, then G should not be derivable, because if you could, then it would be inconsistent. You would then have two statements that contradicted each other in a system. He then proved that you could never formally derive the statement X, which meant that X was a true statement, but since you can't derive it, then there must be something missing in the system. Thus it must be incomplete. Finally, as his knockout punch, he created another formula A that said, GS is consistent. He then goes on to prove that if A is true, then X would be true too, which he uses to prove that the statement A can't be derived. Thus, you cannot prove the consistency of GS using the internal logic of GS. What does this mean? Well, this means that you can't prove the consistency of mathematics using mathematics. This also means that in mathematics, you will find statements that are true, but you can't necessarily prove. One of the facets of this proof, and one that Gödel didn't think people would take so easily, is that this isn't limited to GS. This applies to any system that has arithmetic properties in them. Gödel's proof left mathematicians dumbfounded. Some were confused, frustrated, even angry. They didn't know how to take it. To this day, Gödel's conclusions are still being interpreted. One common interpretation, and pretty famous too, is Stephen Hawking's. He famously ended one of his lectures with this quote:
I am now glad that our search for understanding will never come to an end, and that we will always have the challenge of new discovery. Without it, we would stagnate. Gödel's theorem ensured there would always be a job for mathematicians.